Hi, this video covers section 12.3. We're going to be talking about some of the properties of logarithms. And the very first property we're going to discuss is what we call the product rule. And a couple of things to point out about this rule. The first thing is that just as you might expect, there's got to be a product or a multiplication going on somewhere. And it says that if we take the log of x plus the log of y and we add them together, notice that they have the same base. Both logarithms have the same base, they're both base b. Then we can combine to a single logarithm with the same base. And inside the single logarithm, the argument is the product of the initial two arguments. So if we have log of x plus log of y, we get log of x times y. And just to see how that works out in an example, let's say we wanted to rewrite log base 2 of x plus log base 2 of y as a single logarithm. Well, log base 2 of x plus log base 2 of y. Notice that they have the same base. And when we apply this property, our answer is also going to be log base 2, but we're going to take the product of the arguments x and y. We can also apply this property backwards. If I have the natural log of a product, the product is 5 times x, I can still apply this property with ln, natural log x, because remember that natural log x is equal to log x with what base? Base e. And so applying this backwards, I can say it's a natural log of 5 plus the natural log of x. That's applying in the opposite direction. I can always split a log apart. Okay, if we have a product rule, we must also have a quotient rule. And the quotient rule is similar, except here, when we subtract two logarithms, log of x minus log y is equal to the log of x divided by y. So an example of this being applied is that log base 2 of 40, notice there's base 2, minus log base 2 of 5, again base 2. I can rewrite this as a single logarithm base 2 where I divide the arguments. The argument of 40 divided by the argument of 5. Of course, that simplifies down to log base 2 of 8. And you remember from last section when we introduced logs how we think about logarithms? The logarithm is equal to the power that you raise the base to get the argument. So of course, this is equal to 3. Remembering that 2 to the third power is 8. 3 is the power that you raise 2 to get 8. So that simplifies all the way down to 3. And we can use this property in the reverse order too. I can split up a log into different parts. So if I had the natural log of a, b over c, the first thing that we'll see is that this is equal to the natural log of the numerator, ab, minus the natural log of the denominator. This is by the quotient rule that we just talked about on the last page. And am I done there? Can I keep going? Well, you should notice then that this first part is a place where we can apply the product rule, right? So I could rewrite the first part as the ln of a plus the ln of b. minus the ln of c. Here we're applying the product rule. And so there you go. This is our simplified answer. ln of a plus ln b divided by ln c. Another property is the power rule. And what the power rule allows us to do is that when we have an exponent on our argument, so instead of just log of x, we have log of x raised to some power, what we can do by this property is take the power, the exponent r, and multiply it on the front. And that's what we see here on the other side of the equal sign. We see the power r times the log of x. So in the next example, it says rewrite the following using logarithms of single factors that do not have exponents. Right now, this is not the logarithm of a single factor. It's the logarithm of 16 times x to the 5th times y to the 12th. That's a lot of factors in there. So first of all, I can rewrite this using the product rule. So log base 2 of the first factor plus log base 2 of the x to the 5th factor plus log base 2 of the y to the 12th factor. And what power can I raise 2 to get 16? Well, 2 raised to the 4th power is 16. So log base 2 of 16 is 4. And then using the power rule, I can take both the 5 and the 12, and I can multiply them on the front. So the second term could be rewritten as 5 times log base 2 of x, and the third term could be rewritten as 12 times log base 2 of y. So we have, first we applied the product rule, and then on the second step, when we brought the powers down, we applied the power rule. And there we go. We rewrote this logarithm as a bunch of sum of logarithms that had logarithms of single factors. So let's see if we can come up with some more properties using what we've learned so far. We know that log base 5 of 5 is equal to 1 because you have to raise 5 to the first power to get 5. 5 to the first power equals 5. Well, let's use that fact with what we have over here. We know that log base 5 of 5 to the third, the 5 to the third can be rewritten as 5 times 5 times 5, which using the product rule, I can rewrite this as log base 5 of 5 plus log base 5 of 5 plus log base 5 of 5. That's by the power rule. I'm sorry, the product rule. And then based on what we just wrote over here on the left side, log base 5 of 5 is 1. So each one of these three logs is equal to 1. 1 plus 1 plus 1. So this is equal to 3. And the last one, this was like 5 to the first power. Log base 5 of 5 to the 1 is 1. Notice that basically this exponent here is all that's left when we take the log base 5 of 5 to the 1. It's equal to 1. And log base 5 of 5 to the third is 3. So generalizing that result, down below here we see that log base b of b to the r is equal to r. So here, power 1, here's power 3. We take the log of those exponents, we just get the powers. So here the r, log base b of b to the r becomes r. And why is that? Well, the reason why is because of what we talked about in the last section about logarithmic functions and exponential functions being inverse functions of each other. In other words, if I take r as my input, whatever b to the r, whatever this exponential function does to the input, then when I take the log of it, it undoes what the exponential function did to it, and it gives me back my input that we started with, r. And I can go in the opposite order. If I take the an exponential function and I put into it a log function, because exponential and log functions are inverse functions, they undo each other, and my original input of x becomes my output x. It's like this picture we drew before, where if I took x and I put it into f, out came some new y value, f of x, but if I put that back into the inverse function, it turned it back into x. Well, here it's like r is being put into b to the x, r is being put into b to the x, which makes it b to the r. But if I put b to the r back into the inverse function, log base b of x, I get back r. It's that same concept. And so, seeing how that gets applied here, log base 3 of 3 to the 7th would just be 7. They're both base 3. Natural log, which is log base e of e to the 6th, is 6. 4 raised to the log base 4 of 5 is 5. And e raised to the natural log of 5 is 5. It's just a nice, simple application of properties in the box right there. Well, let's now work on combining natural logarithms using all the properties we've talked about. So if I took a look at this first example here, and I tried to rewrite it as a single logarithm, just kind of see what's going on here. One thing that we can do is we can rewrite this as the natural log of 5 plus the natural log of a. Let's group those together. Those are both positive logarithms. And then if I factor out a negative, I could take the ln of b plus the ln of c. Notice if I distribute the negative back, I get what we started with here. And then, what rule can I apply to both of those groups there in parentheses? Please say the product rule, because they have a log plus a log. So this first one could be rewritten as the log of 5 times a. We have minus. The second one can be rewritten as the log of b times c, or just bc. And are we done here? Well, we're not in a single logarithm, so we need to keep going. What rule can we now use to combine ln of 5a and ln of bc? Since there's a minus, we're going to use the quotient rule. Which would give me the ln of a quotient where the top is the first argument 5a and the bottom is the second argument bc. This is kind of a lengthy process here. We went through 1, 2, 3 steps to get to our final answer. Now if we look back at what we started with, I would argue that once we know how these things work, we can skip these first 2 steps. Notice the ln of 5 and ln a, the 2 positive logs, the 5 and the a are both up top, and then the 2 negative logs, their arguments b and c are in the denominator. So once you've seen one of these, we could try this again. First of all, let's go ahead and take this 1/2 and this 3 and move them to a power so we can apply the other properties. So we have log of x to the 1/2 power plus log y minus log of z to the 3rd power. And then remember, how can we rewrite x to the 1/2? What is that also equal to? That's the square root of x. So I could rewrite this as log of square root x plus log of y minus log of z cubed. And now, using what we did in the last example, what I'm saying is I can combine this into a single log of a quotient. And since the first two logs, log of root x and log of y, are both positive logs, the root x and the y are going to go on the top. And since the last one is a negative log, the z cubed is going to go in the denominator. You go through the steps that we did in the last problem if you wanted to take a few extra steps, but we could also jump right to that. And then we can also work backwards. We could work in the other direction. I could split a log up using all the properties we've talked about. So I could take this first example and I could rewrite it as log base 2 of 32, and because 32 is on the top, and then we have another positive logarithm, log of x to the 7th, that's again base 2, and then the y to the 3rd is down below, so that's going to be a negative log base 2 of y to the 3rd. Hopefully that makes sense. And then just simplifying here, what power, 2 to what power is 32? Well, 2 to the 5th power is equal to 32. So log base 2 of 32 is equal to 5. It's the exponent that we raised 2 to get 32. And then, like we did before, we can take this power, put it on the front, take this power and put it on the front, using the power rule, which gives us 7 log base 2 of x minus 3 log base 2 of y. Okay. So now might be a good time for you to pause the video and try the next one based on what we've been doing. Okay, so hopefully you tried this next problem. If I'm looking at it, I know that I can rewrite this. I can expand it into a bunch of logs. The first one is going to be the log base 5 of a to the 3rd. That's in the numerator. And then we're going to have two negative logs. We're going to have log base 5 of 125 and another negative log base 5 of b to the 4th. Both of these logs are negative because both of their arguments, 125 and b to the 4th, are in the denominator of the original log. And just simplifying again here, the 3 can go to the front. So I can rewrite this as 3 log base 5 of a. 5 to the 3rd power is 125, so this can be written as minus 3, and then minus 4 log base 5 of b. Move that 4 again to the front. So there we go. That's how we expand a logarithm into a sum or difference of many logarithms. And then the last property we're going to look at is what we call the change of base formula. Now, recall that on your calculator there's two log buttons. There's the L and X button, And there's the logx button, which are just two specific logs. The first one is log base e of x, and the second one is the common logarithm. It's log base what? Log base 10 of x. So if I wanted to calculate something like we have here in the first example, base 4, I couldn't do that with my calculator because I only have base e and base 10. Well, that's where it's nice to be able to change the base. And so what this formula says is that if I have the log base b of x, I can change to log base a by taking the log of x divided by the log of the base. So if we apply it to this first example, we can change it to a quotient of logs. Let's make them both log base 10, the common logarithm. And what this says is the top one is log of x, which is the argument of our original log. And so in this case, our argument is 42, so the top is going to be the log of 42. And then the bottom log is the log of b, which is of course our base. And so we're going to have, in this case, the base is 4, so this is going to be divided by the log of 4. And now that they're both base 10s, we can calculate this with our graphing calculator. Take the log of 42 divided by the log of 4. And we get 2.696 approximately if we round to the nearest thousandth. 2.696. And just to show you, I could also do this with natural log. You're going to get the same answer. ln of 42 divided by ln of 4 will also give us the same answer. So we get approximately 2.696. If we try the next one here, this is going to be the log of the argument divided by the log of the base. Calculating that, the log of 3 divided by the log of 5 is equal to about 0.683 if we round. Okay, so that does it for section 12.3. Thank you for your time. We'll see you in class.